In the previous lecture, you have seen, I gave you lecture on emission spectroscopy. This is a special case of emission spectroscopy, which is plasma emission spectroscopy. So again, many things will be repeated here, but we need to know what is plasma emission spectroscopy. How is it different from the atomic emission spectroscopy? So spectroscopy is a branch of science concerned with production and analysis of spectra produced by spectrophotometer. In emission spectroscopy, a sample normally excited by thermal energy. Atoms in the sample absorb thermal energy, causing outer orbital electrons to become excited from their ground state to higher energy orbitals. After a short time, the excited electrons return to ground state. Simultaneously, electromagnetic radiations, normally in the form of light or UV visible range, are emitted. The emitted radiations are analyzed by a spectrograph, which separates various wavelengths. Now, this part you know that atoms are capable of emitting energies. In plasma emission spectroscopy, the exciting medium or agent is plasma. The term plasma in physics means very hot, high temperature ionized gas, sometimes described as the fourth state of the matter. The other three are solid, liquid, and gas. In this method of sample analysis, a plasma source is the basic component. Plasma emission spectroscopy is similar to optical emission spectroscopy in principle, but differs in mechanism. In optical emission spectroscopy, the sample excitation is done by electric arc or spark mechanism. In the temperature range from 3000 to 5000 degrees Celsius. While in plasma emission spectroscopy, the temperature range is 7000 to 900 degrees centigrade. The use of plasma as an atomization source for emission spectroscopy has been developed recently. As a result, the scope of atomic emission spectroscopy has been considerably enhanced by the application of plasma techniques. A plasma again may be defined as a cloud of highly ionized gases composed of electrons, ions, and neutral particles. What is plasma? It is a mixture of electrons, ions, and neutral particles. In plasma, over 1% of the total atoms in a gas are ionized. Plasmas can conduct electricity and are affected by magnetic field. Since it is composed of electrons, it can conduct electricity, and if there is electron movement, that movement will be affected by magnetic fields. These are composed of highly energetic and ionized gases. Typically, in a plasma, over 1% of total atoms in a gas are ionized. Plasmas can conduct electricity and are affected by magnetic fields. These are composed of highly energetic and ionized gases and are produced in inert gases like argon. They are useful not only for dissociation of atom but also for excitation and ionization to give atomic and ionic emissions. In plasma emission spectroscopy, the gas, the usually argon, is ionized by the influence of a strong electrical field, either by direct current or by radio frequency. The sample solution or analyte solution is supplied to the plasma source by a nebulizer assembly. On reaching high temperature plasma, the solution attains this temperature and all types of molecular bonds break down. Free atoms or ions are produced which emit their characteristic spectra. A monochromata assembly is in position after plasma source for isolation of the desired analyte line. The intensity of an analyte line is directly proportional to the concentration of that particular analyte element being analyzed in the sample solution. The detector and readout assembly gives us the concentration of particular element in the sample. Modern instruments being computer controlled, the analysis is very fast and needs little operation skills. Depending on the technique of production, plasma may be of three classes. For example, DC direct current, argon plasma, microwave plasma, and inductively coupled plasma. The ICP is the most widely used due to the mechanical simplicity and operational advantages. Therefore, plasma emission spectroscopy is the method of analysis of various elements in the sample by passing sample solution through plasma, thereby exciting outer orbital electrons of the analyte with simultaneous emission of electromagnetic radiations, sometimes in the form of light, which are then analyzed by means of spectrograph, which separates various wavelengths of the analyte in the sample. Now, you can see the principle of plasma spectroscopy. Here, various species which are generated in this process when analyte is passed through plasma are these. First of all, desolvation of water present in the solution takes place and the analyte becomes solid. Then that solid is vaporized. Solid is itself is vaporized. It comes in the form of gas. That gas is atomized to give element. Then element is ionized to make ion, and then this electron is excited, and within fraction of seconds that will again come to ground state, and as a result of which atomic emission will be obtained. This is the principle or steps in plasma emission spectroscopy. This can be depicted in the form of energy level diagrams also. Now, figure energy level diagrams of atomic transitions. 1 and 2 are excitations. 3 is ionization. 4th is ionization and excitation. 5th is ion emission. And these are wavelengths of emission. 6, 7, 8. 6, 7, and 8. These are atomic emissions. Such a transition is given by the equation E is equal to h nu, where h is Planck's constant. This expression can be written as hc by lambda, where E is the energy, h is Planck's constant, h nu is the frequency, lambda is wavelength, while c is velocity of light. The difference in energy, for example, example 5 is large in comparison to emission. Hence, wavelength for ion emission, lambda d, is short as compared to one for atom, lambda a. Generally, during such multiple transitions, we prefer the first resonance line for the measurement. So from here we will be taking measurements, not from here, because we are going to consider the atomic emission. This is an example for sodium. So they say that, okay, I am reading this. Electronic configuration of sodium may be represented as 1s, 2, 2s, 2p, 3s. So during the process of excitation, an electron from 3s orbit jumps to 3p by absorbing energy of 2.2 electron volts, but when it emits to the ground state, it does at lambda 589 nanometer. The electron on further excitation can go to 4p level and return to 3s ground state at lambda 330 nanometers, but this wavelength is not preferred for analysis. This property makes atomic spectroscopy useful for specific analysis of elements. Now, the process of atomization and excitation. In an atomic emission spectroscopy, which you read before, the sample is subjected to high temperature, high enough not only to cause dissociation of into atoms, but also to cause collisional excitation and ionization of the sample atoms. Such excited atoms decay to lower states through thermal or radiative emission, and intensity of light emitted at a particular wavelength is measured. Generally, for the purpose of atomization and subsequent excitation, three kinds of thermal sources are used to dissociate sample molecule into free atoms, and these are flames, which are used for flame photometry. Graphite furnaces are used for atomic absorption spectroscopy. Electrical discharge is used in atomic emission spectroscopy. Unfortunately, flame and furnaces have not always sufficiently high temperature enough to dissociate many molecules into free atoms. In atomic emission spectroscopy technique, an arc or spark is used to atomize the atom, the analyte. In such electrical discharges, the arc is created by an applied potential across the electrode to produce temperature of around 7500 degrees Kelvin. However, such electrical discharge do not give the desired result for plasma emission spectroscopy. It is therefore necessary to go in for plasma source. Plasma as an excitation source, which is used for plasma emission spectroscopy. A plasma source has high stability and can overcome depressions or interference effects caused by formation of stable compounds and give increased sensitivity of detection. It is simple to operate, especially for liquids which cannot be handled by arc spark source. One does not require An electrode for discharge and contamination with low background emission is avoided. Plasma excitation source can be of different types. First is direct current plasma. You are seeing the diagram here. Description is as follows. DCP plasma source consists of a high voltage discharge between two graphite electrodes. The recent design employs a third electrode, also arranged in an inverted Y shape, which improves the stability of the discharge. The sample is nebulized at a flow rate of 1 ml per minute. Using argon as a carrier gas, the argon ionized by high voltage discharge is able to sustain a current of around 20 amperes indefinitely. The DCP generally has inferior detection limits to inductively coupled plasma. Although DCP is comparatively less expensive than ICP, the graphite electrodes need replacing after a few hours of use. So this is good source, plasma source, still it has some problems. Now, other sources, inductively coupled plasma, ICP. ICP source, the you must see the diagram also. ICP source comprises three concentric silica quartz tubes, each of which is open at the top. Liquid samples are nebulized into an aerosol and fine mist of sample in the form of droplets is introduced into the ICP. The nebulizer argon stream that carries the sample in the form of an aerosol passes through the central tube. The excitation is provided by 2 or 3 turns of metal induction tube through which flows a radio frequency current. Its frequency is around 27 megahertz. The second gas flow of argon of rate between 10 to 15 liters per minute maintains the plasma. It is this gas stream that is excited by radio frequency power. Gas flows in a helical pattern which provides stability and helps to isolate thermally the outside quartz tube. The plasma is initiated by a spark from Telsa coil probe and is thereafter self-sustaining. The plasma itself has a characteristic toroidal donut shape in which the sample is introduced into the relatively cool central hole of the donut. Now, you see this diagram again. Sample aerosol in argon, sample plus this gas is coming from nebulizer, and auxiliary argon is introduced from the side tube. These are concentric quartz tubes. Then these are RF radio frequency coils. From here, this aerosol is subjected to affected by radio frequency, at a result of which it will be atomized and electrons will go to higher energy state and then they will go down, and finally the energy emitted will be analyzed. This is the mode of sample introduction. The sample in the form of a solution is carried into hot plasma by nebulizer system at a flow rate of 1 ml per minute. The most widely used nebulizer system in ICP is crossed flow nebulizer showed in the figure. The sample is forced into the mixing chamber at a flow rate of 1 ml per minute by peristaltic pump and nebulized by a stream of argon flowing at 1 liter per minute. Babington type nebulizer is used for handling slurries that can contain up to 10% solids. This design of nebulizer is less likely to suffer from blockage. Now you see this, both argon and sample will be coming from here, and sample is coming from here, aerosol is coming from here, and both will be mixed here. Okay, stages of process. Argon is circulated through the coaxial tube. When a radio frequency field is applied, argon gas starts circulating around the argon of radio frequency signal. Argon gets charged and produces electrons and the charged argon ions. A spark is applied at the mouth of coaxial tube to produce plasma. Finally, in the last stage, a sample of liquid to be analyzed is injected into the plasma to puncture the plasma and encapsulate the sample at a very high temperature within it. Figure 7 or figure shown below shows the various stages of the process taking place when the sample droplet is introduced into the ICP. Stage 1, only gas is given, then gas comes under the influence of radio frequency, then it is charged, and with the spark plasma is produced, and in the last stage sample is introduced. A radio frequency, a transformation in the sample. A radio frequency field causes ionization and formation of plasma in the region 4. And subsequently, sample aerosol carrying nebulizer flows punches a hole into the plasma. The sample of aerosol is carried into the center of the plasma. The sample undergoes various transformations like dissolution, vaporization, atomization, ionization, and excitation. You know what happens then? Excitation, outer electrons are excited to higher energy state, and we get very high temperature in the plasma. The gas temperature in ICP is around 6273 kelvins. It helps to eliminate chemical interferences. So such high temperature is required to remove chemical interference. The sample inside the plasma remains for 2 milliseconds only. Such duration reduces matrix interferences. The sample in ICP discharge does not travel outside the discharge and experiences a uniform temperature. Emission from plasma is usually polychromatic. Separation is done by monochromator and detection by photomultiplier tube. On account of large number of emission lines, spectral interference can easily be avoided by use of monochromator. The detection limit is in microgram per liter range. The sample concentration should be 5 times the detection limit. The upper limit is known as linear dynamic range. A large LDR needs less dilution. Now, instrumentation. There are 2 basic types of instruments used in plasma emission analysis, namely simultaneous and sequential. multi-element spectrometer. What happens? Simultaneously, many elements can be detected, or sequential multi-element spectrometer. Now let us see what is simultaneous multi-element spectrometer. In this instrument, radiation from plasma enters through a single slit, which is, which is then dispersed by concave reflecting grating. The component wavelengths reach a series of exit slits which isolate the selected emission lines for a specific element. The entrance slits and diffraction grating surfaces are positioned along the circumference of the Rowland circle, the curvature of which is equal to the radius of curvature of concave grating. The light from each exit slit is detected to fall on the cathode of multiplier tube, and one for each spectral line is isolated. The light falling on multiplier tube gives an output which is integrated on a capacitor. Hence, the resulting voltage is converted to concentration of each element present. Light path of the instrument is shown in following figure. This is ICP source, plasma source, and emitted radiation comes out here. And this is the grating which selects one light for each element. It sends light to photomultiplier tubes, and then it is sent to detector. Light path of simultaneous multi-element spectrometer. Multi-channel spectrometers are capable of measuring intensities of the emission lines up to 60 elements simultaneously. To eliminate the effects of possible non-specific background radiation, one or more additional wavelengths may be measured, and the background correction can be achieved by Zeeman or Smith-Heifetz system, or background at each specific wavelength can be subtracted by using vibrating quartz plates, which results in small shift of wavelength. The emission of shifted wavelength is then subtracted from the original value. Advantages. The main advantage is that the modern computational facilities available with the simultaneous analysis may be achieved with better precision than that obtained from a spectrograph using a photographic plate. Thus, results of 25 elements may be obtained within 1 to 2 minutes. Prior to use of plasma excitation, arc and spark sources were used on multi-channel spectrometers, the so-called direct reading instruments. Now, second type of spectrometer is shown here. In this instrument, the plasma is located in the upper center of the spectrometer just above the nebulizer, which is powered by computer-controlled peristaltic pump. Communication with the instrument takes place on a video display, which provides graphics to simplify development of method. This figure shows the light path of thermoelectron 200 ICP spectrometer. Let us read it first, then we will come back on the figure part. Optical system of the instrument. Light from plasma passes through a lens on a mirror M1. The angle of M1 is adjustable under computer control, changing the viewing height of plasma for each analyte. Following M1, the light travels through a monochromator defined by mirror M2 and grating G1. The function of this monochromator is to reduce level of stray light, which may create problem in plasma system. The light then travels through a second monochromator, grating G2 and mirror M3, which improves the resolution. The system provides a resolution of 0.02 nanometers comparable with the emission line width. Before each wavelength scan, the grating locates itself by finding 365 nanometer triplet of a built-in mercury light source. It then moves sequentially to the wavelengths for the elements to be determined. The instrument can also be equipped with the second double monochromator, making it possible to analyze 24 elements per minute. In addition, a high-resolution vacuum monochromator is also available, which extends the wavelength range down to 170 nanometer, enabling elements to be determined which produce emission lines in the vacuum ultraviolet region, such as sulfur. Now we must see the diagram. This is the plasma source. From here, this light comes here. Then this is reflected and goes through slit to M2. M2 is the grating, mirror, and this is the grating. From here, light goes out and passes through second slit, mirror, then again to grating 2 from here, and finally for photo multiplier tube for detection. Analytical method. To produce an analytical method, the operator must select the power level of the plasma, the wavelength of each element, which should be free from spectral interference from background elements which are not desired to be analyzed. The viewing height at which plasma is to be seen for each element. It is sorry. It is also necessary to apply the background correction, and intervals are set using the graphics capability. So these were the different parts of spectroscope or instrument. And now again ICP-AES instrument is composed of important components, for example nebulizer, pumps, spray chamber, sample injector, ICP torch, RF generator, and detector. Nebulizers are devices to convert liquid into aerosols for onboard transmission to plasma. So these two forces are used for breaking up the droplets of samples. Pumps are used to pump liquids into nebulizers. Usually peristaltic pumps are used which do not come in contact with the liquid. Tubing should be dependable and made from appropriate material. Sprayer. The spraying chamber is used to transport liquid droplets into plasma. It is located between nebulizer and torch and removes large droplets. Droplets of 10 micrometer pass through it while it allows extra solution to drain off. Sample injector. The sample is kept in it and via pump it goes into nebulizer. Usually hybrid generator is used for ASSB, BI, Hg, Ge, Pb, Se, Te, Sn. Solid samples are introduced via an arc spark source. This is a schematic diagram of a typical ICP-AES assembly. This is gas comes out from here, sample injector. This is the pump. Both are mixed here in nebulizer and spray chamber, and big droplets are dropped down. Then it goes to ICP torch and RF yani radio frequency generator. From here, the emissions are collected. They go to a spectrometer and photomultiplier tube. This is microprocessor, and then finally this type of graph or a spectra is seen on the display. ICP torch has several temperature zones. Radio frequency generator is there to provide radio frequency of 27 to 12 megahertz. It has capacity to generate 27 to 56 megahertz. Depending on the material to be analyzed, this frequency will be differed. Now detector, photomultiplier tube is used. And finally, the applications of plasma emission spectroscopy. Analysis is considerably simplified by ICP-AES technique. On an average, RF works on 1 to 2 kilovolt wattage, while plasma argon flows at the rate 12 to 15 liters per minute in the auxiliary. Nebulizer unit plasma flow is 1 to 2 liters per minute. Usually traces of metals like copper, iron, magnesium, manganese, calcium, zinc, phosphorus, potassium from beer or wine are best analyzed by this instrument or a spectroscopy. ICP technique can be used to analyze aluminium in blood, copper in brain tissue, selenium in liver, and sodium in breast milk. Trace metals from alloys, steels are also analyzed. Metals such as copper, iron, nickel, silicon from lubricating oils or gasoline can be analyzed at tracer concentrations. ICP techniques can be employed for analysis of agricultural products and foods. In earth sciences, lanthanides in rocks can be analyzed, while in environmental analysis, copper, iron, cadmium, nickel, molybdenum, zinc, and palladium from seawater can be analyzed. The source is able to reproduce atomization conditions with a far greater degree of precision than obtained by classical arc and spark spectroscopy. As a result, spectra are produced for a large number of elements, which makes the plasma source amenable for simultaneous elemental determinations. ICP technique is especially important for multi-element determinations over a wide concentration ranges. This is the table you can see, comparison of atomic spectroscopic methods. The detection limit is better in ICP-AES, while in atomic absorption spectroscopy, it depends upon the kind of metal. For example, analysis of alkali metals, flame emission, or ICP-AES is better. Accuracy is better in AAS than in ICP-AES. AAS is atomic absorption spectroscopy, which I will be telling you later. In ICP-AES, one needs to be highly skilled, while average skill is required in operating AAS, atomic absorption spectroscopy. However, the technique of analysis depends upon several parameters such as matrix, level of analysis, time and number of analyte samples, interferences present, and accuracy. So, no generalized formula can be offered for the selection of a particular method. There are some important or short answer questions also, and their answers. So this was all for plasma emission spectroscopy. Wait a minute, I'm showing you the summary of plasma emission spectroscopy. So process of atomization and excitation can be done by flames, as in flame photometry, graphite furnace, in atomic absorption spectroscopy, electric discharge, as in atomic emission spectroscopy. Flame and furnaces don't have significantly high temperature enough to dissociate many molecules into free atoms. Thus, in AES, an arc or spark is used for atomization, which is created by an applied potential across the electrodes to produce temperatures of 7500 kelvins, but desired results are not obtained. When we use plasma as an excitation source, which are of two types, direct CP and ICP, we get the desired temperatures, and out of these two, ICP is better source. And about ICP instrumentation, there is one simultaneous multi-element spectrometer. Here, intensities of emission lights of up to 60 elements may be measured simultaneously. Results of 25 elements may be obtained within 1 to 2 minutes. And this is wrong, so I'm cutting this. For sequential spectrophotometer, 24 elements per minute can be analyzed. Emission lines up to vacuum UV region, that is this range, can be detected. Important components of ICP-AES are nebulizer, pumps, sprayer, sample injector, ICP torch, radio frequency generator, PMT. And this was the summary of plasma emission spectroscopy instrumentation. And this is all for this topic now.